just for the benefit of the recording, we are looking at ANSYS. We're going to be using Horizon, but first today we're really going to be looking at meshing procedures and the mesh. What does the mesh do? How the hell does the mesh even work? What is the mesh? And so some of you may think, well, this is just obvious, but some of you may not. And what I really wanted to do is just slowly take some small steps in this process. There is some notes that I've written for you that will support this as well. So if I butcher any of the equations that's in there, apologies. It's just Visio for some reason does not like me writing particular equation straight into it. I need to get a pen, really, like the normal digitized pens, so I can just write it directly. Okay. So the mesh, you've seen it 1,000,001 times. You must have seen this millions of times. This is typical to what a mesh would look like. It's a series of what looks to be lines, construction points, things like that. One of the most accurate terms I ever heard of somebody describing the behavior of a mesh is a spider's web. Spider's web is a very good one. If you imagine that you take your hand, place your hand into a spider's web, and you look at the individual threads around that spider's web, they will elasticate and they will extend unless you keep pushing until you get past that elastic region and you get to failure, where at that point it will just break. It's a very good analogy of what the mesh will do. If you consider that as the mesh, that means that if you create a piece of geometry, then you create a mesh to go onto it. It's only a version of the geometry that you've done. You do need to keep these things in mind. But it's all right looking at all these, but what do they really do? What is it exactly that we're looking at? This one's a cracking example, actually, and I'm going to use this to my advantage. So if you take this, we've got collections of what appears to be lines, triangles, rectangles, and all different types of things. We have tetrahedral, and we have pyramid, and we have hexagonal methods of applying it. But again, still doesn't explain exactly what it is. In fact, in many ways you could say that's confusing even more. So when we got to this point, please don't think I am being patronizing, because I'm sure as hell not. Let me just add all these in. I'm just going to pull this down. It's a benefit to just pull this down because I'm going to explain this a little bit more. Right. So our spot. This is our black spot. If we then put this into something like a geometric space. So let's say CAD. Let's say when we were setting the robot arm, for example, we needed an origin. We needed a position. When we have a position, the position is given by a key set of coordinates. In our case, the key set of coordinates are X and Y. Now this is just for a two-dimensional degree of freedom node. These are known as nodes. These are known as representations. Now I've just put P1 as in point 1. But this is a representation. This is a single degree, this is a single node representation. What we can do with that is some amazing things, but at this point all it really does is it holds a few important bits of data. It tells us where it sits in space, and at the moment, in this case, not much more than that. However, as you'll notice from beneath there, if I use this method and then apply it across to here, we've now got two nodes that sit in position. And then what you could easily say, if this is going to be a point, for argument's sake, this simply becomes point 2. Between the 2 points, we actually still don't really have anything. We've got 2 separate coordinates. And the magic of what we're about to start looking at only really happens when we bring in an element. These elements will connect these two together. At this point, we're now at a very exciting point. We're now at a position where what we can do is start to see what happens if I move point 2 across. But at the minute, there's nothing that will constrain that. It still holds its own data set. All it really does is it will just be a line and a spot. However, what if then I drop in onto this element? What if I then drop in? Now I hate doing this, but it's the only way I can do it. E. Really, what I'm trying to go for is epsilon, but it's Young's modulus. That's what I'm going for. So what if I drop in Young's modulus? The overall stress over strain of a material itself. But tell the system it has no behavior on it, but this linear behavior between it is that maximum Young's modulus. It's that elastication of that material. It's that natural damping that you can extract from that material. Now, this is all still hypothetical because we've still not really got any geometry there. And this is just relationship between two nodes, nothing more. What you could easily say is, if we wanted to know, well, before I jump too quickly forwards, by that respect, if I then place a force onto there, I will do this, it took me forever to get this right yesterday. If I put a force onto there, now again, all I'm doing here is just describing where that's coming. If I place a force onto this end and I fix P1, so P1 has zero displacement, it cannot move, it is ultimately constrained, it is, for argument's sake, an immovable object. However, node 2 has a force applied to it. If I take this force, let's say for argument's sake it displaces this distance, what we essentially end up with is a new position. So if we've ended up with a new position, this gets so good it must be fattening. If I there we go. Oh, that's working out a little bit better than it did yesterday. Right, so if I look at these two between it, it's moved a particular distance. So here, that should be really delta L, but so it's the new length. And then we can have L. What it's actually done is it's given us a new length by an original length. And this really is tapping back into your first year mechanics, or for some nowadays, even high school A levels. What it's actually given us is strain. Delta L over L. It gives us the strain of what has happened within our single set of values. Again, still not a geometric representation of what's really happening. It just gives us that overall strain based on the Young's modulus, nothing more. However, what it also gives us though is a way to track displacement between the strain that's come. We can now simply say that this position has been updated to here. So now what we've got is a way of tracking something deforming. We've got a way of looking at strain that's occurred from it. Because we've got Young's modulus in there. Now, for those of you who used FEA before, I'll bet you any money you've gone straight in there and gone, right, I'll use steel, gone in, and then hit force and run. What it's actually what you've actually selected is you've given it that all-important value. That's why anytime you run an FEA, if you've not selected a material, it will just fall on its backside. It will just say, what are you trying to do? I cannot do this. So, now I am, again, if I am confusing anybody, I do apologize. So, In our simple two node element, so one-dimensional element, what we've essentially got now is we've got our strain, we've got our Young's modulus, and Young's modulus is calculated by stress over strain. So in essence, what you're doing when you're providing this, you're providing what this must be. If you've got strain, then you've got stress. So in essence, you've got your maximum stresses, you've got your maximum strains, you've got a displacement that can be recorded. You've also, more importantly, got a way to track back if your Young's modulus is correct, because you can calculate out what you're getting. You can also physically test what you're getting to actually get your real Young's modulus back. Then what you'll do is map all three against each other. You essentially close the loop, and that is what they call full validation. Verification is what we're going to do here. We're going to calculate out a maximum stress of a truss. We're going to build it in an FEA system, and then we're going to look at what happens. Right. So now this technically has 2 degrees of freedom, X and Y. It doesn't really tell us a bit more than that. But if you think this is this calculation in the X coordinate, you must keep that in mind. This calculation happens in the X coordinate. A good representation of this, so what I'm going to do is just shift this back. I just want to remove these off, just because all these little bits and bobs all over the place does get a little bit confusing. So now I don't know who is interested in this, but it is a fascinating topic. But if we replace this, if we replace our line by putting in a spring. Now, again, you have to forgive me with this. So if we just think of this element as a spring, just for a minute, you know from your own experience that when you apply a force to this, it's only going to react under a linear-based element. So if I attempt to bend this, bend the spring at that particular point, it just won't do. It won't react like the normal. It's only going to move in a linear fashion. What this system does is it does attach the Young's modulus to that spring. However, what it can also do within that spring is it can bring in natural damping and elasticity. So when you actually look at FEA packages, be it Abacus, which is the biggest one that's attached to CATIA, be it ANSYS, which is very, very popular and industry based, or be it COMSOL, which is very popular nuclear based or in academia, they all three do not represent their behaviors of elements with E. They actually represent it with K. Now they literally represent it with K because they know these as hard springs and soft springs. Soft springs, we're probably not going to touch much on this. Soft springs allows you to model the elasticity of skin or something organic. There's a lot of predefined data that needs to be in there, and it can be incredibly confusing. So with this, what we're going to be doing is we're going to be staying with hard springs. Just for your information, we're going to be staying with hard springs, and what we'll do is I'll just put that node back. So what we got is that behavior. Now if we just quickly reflect back to the drawings, it's a lot more complicated than a simple line in between. Now what you've got to remember on this is what we're actually looking at is just one of these. That's all we're looking at. We're just describing how that behavior occurs, nothing more. So this gets even more interesting. If this displaces by Newton's laws, what we can say, what we could propose is that K will be equal to U1 plus minus U2. I'm butchering some of these equations. I'm going to show you the notes itself now because I hate how that looks. But anyway. So with that in mind, it means that if we've got an original distance, we've got a secondary distance, that's going to affect the K value. We've got a way to be able to pull the strain out. We've got a way to be able to relate that back to the spring stiffness. We've got an overall way of displacement and understanding how these two nodes talk to each other. Now, I will get to a big point with this, so please don't think that I'm just stringing you along. Now, let's bring this in. Let's bring in another node. So if I get rid of that, not rid of it, sorry, if I drop in another node. Now, these are the most common ones. These are really, really common. Those of you who've used SolidWorks before, SolidWorks only has the ability to give you triangulated elements. And it's been criticized quite heavily because of that. But SolidWorks never counts itself as an FEA package. Not really, not in the comparison of big things. Bigger softwares can have multi-mixes, so you can have your four hexagonal, you can have your hexagonal structures, you can have your triangulated structures, you can have trapezoid structures. It's crazy the amount of different variations you can get, and a lot of it's known as adaptive performances. Anyway, so we're now added one in, and this is as simple as it's going to sound. If I copy that in and paste that above, now what I do is I say, right, we have P3. So we've now got P3. We know that Young's modulus is attached. It is attached equally all throughout. You don't decide this. It just says, right, this is Young's modulus on all elements that's there. But this is for volumetric materials, isometric materials. So basically, the Young's modulus is equal in all three component directions. Now, if we want to describe how this thing will move, if something's applied to it, if we want to be able to describe how it moves and how it performs, what we can essentially do is we can say, this is to describe the three-dimensional element of this. So what we can actually say is, let's call this E1, or PN I'll call it. Again, I'll show you the notes, it's just I can't write specific symbols, which is a little bit annoying. So I've got P1 of XY, and all this simply does is we can say P1 X, Y, K. Now K and P can relate with each other, because P will give a description of where it moves, K will restrict P to move, but P will update to K where it's actually moved to. So you have these in essence running in the same format. So K is equal throughout the entire thing in our example, but if you were doing something like a carbon fiber or something like that, your K value will be changing. And in this module, in this section of the module, we will be looking at carbon fiber. So we'll be pushing our systems as much as we humanly can. And I'll also be discussing how we can, what they call, erode mesh. But let's just get to this first. So now what we got is an overall descriptive way to give us how this thing moves. Simple key point of the displacement itself. And you do look and you go, well, that P1 to K, it's very, very confusing. It is confusing. It is confusing. And to make things worse, if we consider going back to K, bring this back into here. I just realised I put something there which I shouldn't have done. That is my fault. Apologies. So it should be minus, and we'll go U1 to U2. Oh, U2 minus U1. Apologies. U2 minus U1. And this will give us an overall resultant of whatever force is happening. But this is in a single direction. Now, if we take these key forces that have come out, now these are all an occurrence of the displacement that's moved over our strain that's happened, all running in line with Young's modulus. And these are just a summative way of being able to represent them as small as humanly possible. Because you can imagine writing all these out from scratch. Well, writing all these out in their true format would be a lot larger than what we've got right now. So, excuse me. If we just bring this down, now what I'm going to try and do is describe how in force 1, so let's say for argument's sake that we have a displacement in this direction. In force 1 we end up, apologies, I'll go in this direction instead. In force 1 we end up with a negative. It's moving to the negative component. In force 2, so x and y, so we'll have a force 2 for this. We'll end up with a repeat of the same thing, but not in that negative component. This relies on, well, this enables the balance to occur between both force sets. Now that's just single nodal forces, just between two, because don't forget at this point we're still only in 2 dimensions. If you look here, we end up with a simultaneous equation, straight away into simultaneous equation. And what I might do is just drag the notes in for this, just because I'll end up butchering a matrix. So let's just bring this in. Again, these are all on Blackboard, so they are there, don't worry. So you see there, we've gone from that nodal force. We then move into the nodal matrix. Now, this is purely because it is a simultaneous equation. So we expand this out and we end up with this key matrix. If you then look at this as a spring behavior, what you end up with is a so-called stiffness matrix. What it actually does is it describes that node in its ability to be able to move in all of the 2 component sets that are there. So when you rearrange, the rearranged equation of this, apologies, sits like this. But this is only on 2, this is only on 1 node. Now if I snap this back across and you imagine, whoops, and put that back off there. If you wanted to make this 3-dimensional, what you're essentially doing here is you're expanding on this here and here and here. Now what we saw a moment ago was a 2x2 matrix. If we have a 3rd degree of freedom, what we end up with is an extra U, but we also end up with an extra force output. This becomes further stiffness matrices. So in other words, now what we've got is a way to describe how it can move in X, Y, and Z, how it's going to extend in X, Y, and Z, and its way to displace in X, Y, and Z. Now if we just quickly reflect back to here, now just discussing this, the big point that I wanted to make, the big point that I wanted you to be clear about is, let's just think back to this being a spring. Everywhere where you see a line now is a spring. If a spring sits there and it's extended, what if it fails halfway between? So what if it actually fails somewhere like at that point? What does it do? And what it does is it doesn't see it. The resolution behavior of a mesh, it will not see it. What you end up with is a way to be able to do a design, pass it through all the FEA analysis, put it through prototype, and it'd be the most dangerous thing in the world. So depending on what it is, if it's a bracket for a vehicle of any types, and if anybody's used the default mesh, what this actually does is it allows them to pass off a part which is incredibly dangerous, which could lead to death, God forbid, but death. But you've instantly got a point here where it can fail. Now, a lot of people have said before, yeah, but these softwares do boast themselves to be 90, I think something at the moment, something like 99.7% accurate. They do, that's right. But what people will do is they will often spend days, weeks, sometimes months building the most efficient meshing representation that they can. Because from the start, from the very, very first steps of setting up a mesh, it is flawed. You're fighting against the tide in many ways. So these crazy people who suggest that FEA will do away with prototypes are mad. It is absolute madness. There is no way at this point that FEA will do away with prototypes, because if that is still a possibility, a point of failure, it means without a prototype you won't be able to iron down to these possible problems. There are many, many ways. I mean, you've got meshes which will adapt, you've got expandable meshes, you've got all different meshes that occur. However, they are all still fundamentally flawed from the start, of that they cannot give a true representation of what the geometry is doing. So when you're actually seeing these meshes, when you're actually seeing these processes, what you're actually looking at is a version of that geometry. And don't get me wrong, I don't want to take away from anybody's incredible work that they've done, but do always keep in mind what this thing actually does and how it actually functions. So the price that you pay for FEA softwares actually comes in what they call the solver, which is this meshing procedure, the all-important meshing procedure. As I said, these notes do go through this. I will be uploading these to Blackboard. Well, not I will be. They are uploaded to Blackboard. Do take a look through them if you are interested. I do have more reading behind this if anybody's interested to learn even more about the mesh. This, by the way, is not FEA. This is what's called FEM, so finite element method. This is what gave birth to FEA. Do please make sure that you do not get the two mixed up, because in this really anal society at the moment, you get the two mixed up and you'll also get slaughtered for that. So FEM is a procedure to create the meshing procedures that we are going to apply, that we're going to use. FEA is the finite element method analysis, and it's the process of using these techniques that have been designed, and we're applying these to solve a bigger problem. Now, the first problem we're going to work through is dead straightforward. The beauty is on the first problem is it's the most common one, and as far as I understood, I could never get this confirmed, so I think this is still very much a legend or an old wives' tale. As far as I understand, this is where the finite element method really was first born, in the idea of that, could we not automate the process of solving trusses? Now, when I looked online, I did find a record of a think tank in Cambridge University in 1973, I think it was, and they were discussing solving a car driving over a bridge. Now, if you think a straight bridge, fine, straight is dead simple. But what if you have a bridge that drives over a river? What you've got is an archway. how do you actually solve that process? And that's what gave birth to the idea of why not go back to the actual geometry, and why not start to subdivide that geometry into linear calculated pieces like this. And that is what they were discussing, but I can't find an earlier representation of when that was done. But I do know that they were one of the first to really start discussing the use of what's not now commonly known as the stiffness matrix, which is what we were just discussing then. Right, so in true fashion, what I'm going to do is I'm going to set you a little test. So I'm just going to I've just set a new graph. And if I place, come on. Place this onto here, and then yeah. So that is what we're going to try and solve. Now, I'm not going to put anybody on the spot, so please don't panic if I'm going to put anybody on the spot. But what I'm going to do is give you 4 minutes to solve the key elements for it. What we need is the maximum stress. Oh, excuse me. I need you to solve for stresses around D. So this will be D to E and C to D. These key elements here, and that is what we're going to try and prove. So again, I need you to solve the resultant for C to D and also E to D. And then what we're going to do is we're going to try and build this onto ANSYS. And we're going to look at how to actually construct something dead straightforward like this. So again, I'll give you until 11:45, so that's 3 minutes. I'll actually pause just because it'll be awkward just leaving that on. So I'll just pause for a minute, hit back onto record. As I said, I'm not going to pull teeth on that too much. It was just a little bit of a brain exercise for you all. As I said, these are on the notes, I think I've actually freed these up, so I might have just made myself look a total idiot with that one. By my calculations, F to D to E resultant at 18 kilonewtons, and that, so if it's D to E, so if we're going D to E, we know that that's compressive force, because obviously it draws down, and these 2 points will be compression between each other, so we know that's a compressive force. And from C to D, so C to D, we know that that is 15 kilonewtons, and we know that that is going to be tension. So that's a force resultant as opposed to tension. So what we're going to do is we're going to build up our example to just look at that. Is this any true representation? For those of you who are confident with this, please do fire ahead. You know, I'm doing a truss. There's no reason why you couldn't build up a three-dimensional space. I do want to take some nice steady time. I got some great feedback yesterday from some students. And this is a nice dry run as well, because I myself am also using Horizon today. This is going to take a few minutes, so when we do this, let me minimize that, and let me minimize that, and let's move into building our model to give us a representation of what's happening. So I've opened up Horizon. Now, I always refer to this as ANSYS. Apologies, I can lead to a lot of confusion with this. This is purely because it was always branded ANSYS, always just ANSYS. Then they rebranded the terminology for it. They called it Workbench. This big black mark here is supposed to be a giant A. But yes, so we're actually working on Workbench 19.1. If you've not logged into Horizon, please log into Horizon now. And what I want you to do is double click Workbench. Can you feed back to me if it's not running or if something's not working? This is an ultimate test of things working. We had a few issues yesterday, but we were able to resolve them, which was well, anytime resolving issues is phenomenal news. When you run it, I'm not going to go running into this feat first. I do want to wait for everybody to get something fresh and up and running. This is what you should be getting when you run it. It should open straight into this. Now, it will take a few minutes, so that's what I mean. I'm just going to go steady away. This is a nice intro to getting FEA running and getting comfortable and confident with FEA. So that's why this week we can just give that extra bit of flexibility to get the software running. So again, if you've not done already, please double click Workbench 19.1 and then give it a moment. Now again, we're running through Horizon. I myself am running through Horizon. So I need to make so we can, at least we can get a true measurement of how it's all working out for everyone. If anybody has any issues, please do post it in the chat or something just to let me know. So for argument's sake, what I'll do is I'll just give it 2 more minutes. Let's have a look. Right, so to recording that it's not running. So what I'm going to do, just to check that it's for the license, I'm going to, yes, Max, just got the very same response from somebody else as well. What I'm going to do to see if this is a license restriction, I'm going to switch mine off, and that will essentially free up a license. Can I ask you all to just try and run it again? Because I'm not sure if that's a license restriction. Now, if I switch off, what it'll do is it'll deactivate me from being on there. So I'll just deactivate my function, totally out, and right, I'm totally off. Can you give that a dry run and see if any of you guys can get it running? No, I have an older version of ANSYS on my actual PC, so it won't look any different to what we're going to do. All the tool functions are still there, but you'll be running a more up-to-date version. That's you guys who've been having the trouble with getting this loaded, have you had any luck by me switching off my licensing? That is not good news then. That means we could be down to a number of license restrictions. Right. Apologies, guys. I'll get onto that straight away after this because we can't have that. Brilliant. So this is probably me that's messing it all up. That's great news. Finally, sorry to put you on the spot, Max. Has it worked for you? Okay. As I said, I try to use this session so we can try and flesh out any mechanical failures or possible things that can be going wrong. I wonder what that is. I will chase that up today because that's got me thinking. Shouldn't have. That's yeah. Anyway. Okay. I'm going to push on just these drawings a little bit. If you do get a resolve on that, Max, please will you just drop a message in the chat, because I am curious to know if that gets resolved. Right. So, the truss. Our trusty truss. Not the best drawing. Well, I suppose it is the best drawing. Got the dimensions to it. We know the length of it. We know where everything's sitting on it. We know key points for it. That's how we're able to calculate out where it was going. So, I'm going to minimize. And I'm going to now build me a representation. To the left side, analysis systems. And I know Akinol has gone through this, and I know Graham's gone through bits of it with you guys, but not everybody will be aware of these, so I do just want to give a bit of appreciation what's there. Now, the component systems, we're not going to really touch with this, so I'm going to minimize that for the moment. These are my key targeting areas. Design assessment, anybody who's into topological optimization or wants to use topological optimization, that is your best friend. It will give you feedback. Personally, the ones that I've seen that have come out of CATIA and also come out of, funnily enough, Inventor, them two topological optimization tools are phenomenal. They're a phenomenal resource, and they will give you some very good results. As you can imagine, it goes down. We've got the typical buckling, the electrical responses, explicit dynamics. Now, this one we will be looking at. This allows us to simulate things like bullets traveling through the air. Fluid flow. A lot of people have said to me before, why is there 3 solving methods? And it's just because when ANSYS sees a possibility, they just soak it up so they can become the center of all attention. Harmonic acoustics, harmonic responses, as ever, the typical stuff that you've been looking for when you come to this type of stuff. But what we are going to be looking at is a static structural today. This is because we know what the maximum force should be on our truss example. Because we know that the structure of it, and interestingly, a lot of people have said, well, we never calculated a material to it. That's because the force that's applied will be applied to any material. So what I mean is, if there is 18 kilonewtons there, it will be 18 kilonewtons applied to titanium, applied to steel. It would still be the same force regardless, because it's all down on geometric representation. Right, so what I'm going to do is drag and drop, left click, get my finger on the left click, drag across, drop it into, you see where you got the construction lines. If I drag it in, you see there it says create standalone system. Keep your finger on that left click, let go and drop. Now what we've got is the overall setup for our all important structural analysis. So I'm just going to call this truss. Today I wasn't really going to take a good look at the engineering data as of yet. This is our engineering materials library. We are going to look at this, but I think I'm going to go in a bit more deeper onto this next week, onto that material data. This is where we'll find all the different variations that ANSYS offers, all the different options that ANSYS offers. It's a really good resource for things like that. So, but what I'm going to do is just leave that for the minute. I'm going to concentrate on our truss, because don't forget, for the result we're looking at, material is irrelevant, because we're looking to see if we've calculated correct from our assumption of 15 kilonewtons and 18 kilonewtons. Are we in that ballpark? And I know what you're all thinking. You're probably thinking, well, obviously it's going to work out. It doesn't work out like you'd think. So what I'm going to do is right click. Now when I right click, it gives me an all over option. I can import geometry from other things. If I have a CAD file, I can import it. If the CAD file's been done right, If it's been drawn with some good skill and good procedure, then I can do that, not a problem. If it's a surface, so those of you who've been sitting my surface modeling module, when we've talked about preparing the best type of surface, this is the reason why. The translation across. Translation is still the biggest issue in the world. You can even get import cleanup translation tools. And there's now companies who sell softwares that just recreate the design tree. So there's all different types of things that sit within that. But what I'm going to do is scroll across. I'm not going to use space claim. The only reason I don't use space claim is I've not really used it. That's all it is. It's for those of you who are Autodesk based, the 3ds Max, Maya, all function on NURB representation. So does space claim, but I'm not going to use it just because I'm not familiar with it. So I use the typical design modeler geometry. Give it a minute or two. Typically, this is a really old school type of interface. The interface that you're seeing, your typical XYZ planes. Oh, magic! What was happening there? What I'd like to do then, if you don't mind guys, I'd just like to quickly jump back out of this and then quickly reset that back up. I'm just going to delete this. And I can quickly reset that back up if you don't mind, just because then at least everybody's up to speed. So again, I left clicked, dragged and dropped a static structural, went to geometry, right click on the geometry, new design modeler geometry, and that's it. That's where we're up to. So it comes in, typical output, XYZ planes. So again, you can see there as it spins around, it tries to give you a crappy representation of where everything's sitting. Now what we're going to do is a truss. So we're going to use ANSYS to its advantage here. A lot of other softwares do the exact same thing as well. A lot of bigger FEA softwares, again, Abacus, ANSYS, COMSOL, all do the same thing. Now, the one thing that's always irritated me with this, it'll always come in meters. So if I go to units, I'm just going to change this. Oh no, in fact, sorry, no I'm not. We are in meters here, so there's no point in me actually changing anything. If you do want to change, no, units are here. Right, so I'm going to now attempt to draw. So on XY plane, with it selected, I'm going to go to sketching and go line. Now that, for anybody who's CAD savvy, you'll sit there and go, wow, that's very anticlimactic. And it really is not the best in the world, but it allows us to build the all-important geometries that we're interested in. Now, if I move my cursor around, it's still in that trimetric view, but if I right-click and then go look at, it will look at the plane that I last selected. And what I'm now going to do is start to draw the part. Now, if I bring my cursor over it, you'll notice, I don't know whether you guys can see this, but if you bring your cursor over a key axis, the axes will glow and you'll end up with what looks to be like a tiny rectangle that's attached to it. That's just to note that it's going to snap it to the origin point. What I want it to do is snap to this center here. Left click, draw a diagonal line. Then I'm going to come from this point here. See how the rectangles appeared on the end? Left click again, bring that all the way across. For those of you who have used Inventor, CATIA, SolidWorks, and anything like that, you will know that the systems often bring you up a vertical and a horizontal marker to tell you if the line's going to be marked out like that. You'll notice on here it's giving me a massive H. Massive H is the equivalent of what you get used to in the typical CAD system. So I'm going to left click again, because you'll see now I'm on the key axis component of Y. You can see it's glowing red. So I'm going to left click, and then it finishes the points. Now what I want to do is do one more line from there to there. See the V that's already been marked, so it's telling me now it will be a vertical line when it's applied. And that is the overall outside. So quickly on this geometry, we know it's 4 by 6. This will move in its key movement just because of how these are all connected. I'll come back to add the other lines in just a moment. What I need now though is dimensions, just to give me an idea. And I like to go steady on this just because we're all used to dimension appearing, quick update, done. Not on here. I'm going to go dimensions. I'm going to use general. Left click. Left click. Left click. Left click. So you click it on, and you click it again, and you've got to click it to apply it. Now what you'll see is it comes in as V1 and H1, and you go, wow, that's really crap. Why is it not giving us was it not displaying the value? If you look down the left side here, right at the bottom, you'll know that we've got display. If I pull that off, I mean, I can put them both on if I want. I don't want them both on, just one display. And you look to the left at the bottom, this here is where all the values are changed. You cannot click on the screen to update the dimension. It just really makes you appreciate what you're used to if you are a CAD person. It makes you appreciate what you're actually used to, because this is a little bit clunky when it comes to putting in important dimensions. So we know from the drawing it's 4 by 6. And I'm just gonna I nearly rushed then, apologies, nearly rushed then. Let me just go back. So 2 minutes. So 2 minutes, apologies, yeah. Now if I want to zoom to a particular area, I've just kept saying right click, it was left click. If I right click, keep my finger on it, and then pull a screen across like this, and then let go, it'll zoom to area. That is just a shortcut that's really, really useful, really useful. Now I know that the members which move up the actual part, these are all set at 2 meters apart. So what I'm going to do is go back to draw. I'm going to go to line, and then I'm going to bring this line across. Now if I highlight to it, what it will do is it will go pink. That pink is the same as the snap function in any particular CAD system. So I'm going to left click, drag it down, and you see that all important V trying to appear. I left click, and then I'm going to do the same again. Left click, bring it down, and it's in V, so left click again. And then if I go to dimensions, and all I'm going to do now is I want to give a representation of where that sits. What I'm looking to try and do is just put a dimension on the point of the interfaces. So I'm not going for the line, I'm going for the trouble is, on this as a recorded screen, you can't really see that where it's looking now. Oh, they're saying that, look at the bottom side of my cursor, you'll see that highlighted point position there, and it's telling me I'm on the point. So I left click on the point, again, just bring it in, left click on the point, and then bring that there. I'm going to change this in a moment. if you're having trouble snapping to line, it should be automatically snapping to line, is it not? Again, I'm just going to add this point on to a second point. Oh, that went horribly wrong. Like that. There we go. I will get back to you on why that's not snapped, just because, let's have a look. Where check your tools above. All these tools up here are the selection tools. And just see if you've got all your tools activated. Because you may have not all your tools activated within it. But it should be selecting that way. But give it a go and then just give me a shout. Have you got your, oh yeah, have you got your key pointer? Something for you to try. Right. So my lines are snapped. I've got the all important members in position. The other lines I'm not fussed about yet. These members, I knew that these members were vertical. So first things first, let's change this. Based on the original drawing, we know it's 2 meters. So let's bring this out and let's go 2. And again, let's come to the other side of this and then let's set that to 2. And again, let's just quickly look at these final triangulations coming from top left to F, top left. So it's A to F, B to E. So in this case, I'm going to go draw. And this is easy now. All I need to do, bring it into this corner. Snap it to that corner, into that corner, and into that corner. I'm going to use lookout. There we go. So that is what you should get. Anybody struggled to get that? Navigating your way around this is a bit of, as a modelling tool like this is a little bit of a pain in the backside. If you're lucky and you have been working on CAD system where you've got a 3D drawing, for example 3D sketch, you can actually output a 3D sketch for it to be this. So you could do this on a CAD system if you would prefer, and you can import the sketch itself. You can do all types of crazy things. If anybody's interested in doing that for anything they're working on, anything triangulated, chassis frame based, anything like that, give me a shout. I can show you how to get that moving across. I'll gladly set up a bit of an extra video just to show you that if anybody's interested in it. So let's come back to it. So what do we know about a shaft? What do we know about a truss? To be fair, we don't know the Young's modulus. We don't need to know the Young's modulus, not to solve the forces that are occurring on it. We know it has a second motive area. So if we're going to do a truss, we're going to have to apply a second motive area. But we don't know what it needs to be. So what we'll do is we'll use ANSYS as default. We're going to use ANSYS as default. And we're going to set this drawing up as our sweep point, if you will. Oh, excuse me, I keep burping. Oh. So first thing we need to do is we need to tell ANSYS that this isn't just a drawing anymore. We want to call this geometry. And it's a very sneaky trick that was set up a few years ago, and since then it's set up like wildfire, because originally you had to go about this quite a bit differently. Some of the notes I'm putting them onto Blackboard. Do take a look at them because they are old school way of doing it as well. So you'll just appreciate what we're doing here. So I'm going to go concept. Now it says, on my concept, it's literally saying, how do you want to set up your geometry? Do you want to say there's a piece of geometry on a line? Do you want to say it's on a sketch? Do you want to say it's on a curve? Or do you just want to say this surface is my geometry? We're going to take lines from a sketch. Now be careful here. Millions of people in the past got this problem. I did this at first when I first learned how to do this. And you kind of go, shit. What you're actually looking to do is select them all in one go. And this comes from anybody who has got a lot of experience in CAD. You'll always know, if you want to select an entire sketch in one go, go to the design tree. Click on the sketch. Everything's selected in one go. If you try to click on the screen itself, it's going to pick up individual members, then you're going to press Control, going to try and select all, and you sat there for ages, wasting time. Use the design tree. It's a great way of being able to execute exactly what you're doing. So from there, I'm going to click Apply, and then, this is a bit annoying. It's always been like this. Annoys the living shite out of me, but it is what it is. If I click Generate, what you'll see now is lines. You'll see vectors. This is ANSYS' presumption as to vectors and where they're moving. And it's all based on how I drew the lines. So I can draw the lines to try and give me some... Basically, for this, it doesn't matter for what I'm doing, because I'm going to say how everything's going to work anyway. But that's what, in essence, what it's doing. It's showing me how I drew my lines originally. Because you see there, I went from A to B. Was it A to B? A to F, B to E. So A to F, B to E. And you can see them all important lines and how they were put on. So it's a way of tracking back, but it's them trying to offer you even more option, but it's not really anything that'll be useful for us. Right, so we've now told the system we've got geometry. We've got something we can work to. Now what the system needs to know is what is that all-important second moment of area. Or else when we go to mesh this, it'll just go, you've done a line. Can't give you much from a line. So what I'll do is go to Tools. I always get this one mixed up. Always get this one mixed up. Oh, there we go. So you see we're on Concept. I'm going to come a little bit further down. Keep going down. Keep going down. Cross section. What is your cross section? We could do circular. We could do a rectangular box section. We could do Z sections, L sections, anything that you really want to do. It allows you to do some really cool stuff. It's quite impressive, and it is quite old, is this. So I'm going to go circular tube, and then that's what it gives you. And this, I do find this really confusing. Just gives me that, and you go, yeah, that tells me nothing. You look to the left, you go the physics of the area, you go okay, and we look there, we got 10 mil radii inner, and we've got 22 radii outer in meters. If you know your cross section, so I'm looking at you, Formula student guys. If you know your cross section of your frame, of your chassis, put it into there. This thing will build it in one hit, tell you exactly where everything's going to be, and it allows you to elaborate even further. It's crazy what this can do. Right, so again, right, I come to the end of this and hit generate, and you go, right, everything's gone. So what I'll do is go right click, and I'm going to say look at again, and you go, okay, so what I'll do is click onto my sketch. And you can see that, I don't know if you saw that then, you see down here this little dot, that is our cross-sectional pipe. So if I click back on, you see there, it tries to zoom in and out to give you a good insight as to where everything's sitting. But that's what it's doing. Annoyingly, still, it does not know that that sketch and that cross-section are going to work together. We still need to tell it that cross-section and this sketch are going to work together. This is one of the reasons that we went to make a geometry by lines. If I come down to my all-important part and body tree, you notice I've got line body. Left click onto line body, there. Tells you how many lines are there, how many edges are there, how many vertices are there, how many joints, how you can do, talk about the topological methods between each joint. If you are formula student based, I do refer to you guys a lot because I know you guys do. If you are interested at the behaviours around these joints, failures around these joints, it will try and give you some good representation. So this could be a good way to do torsional stressing around the actual chassis itself. You could do quite a bit of force to the front to give you some type of result for impact analysis. The trouble is transient can be tricky when it comes to this. It has to be quite static structural. However, see where I've got cross section? All it's saying is I've got a line geometry, but there's nothing telling me what it actually is. Left click, tubular, circular tube 1, and then go to generate. Now, see all the green ticks? It's now saying I've got everything I need. You don't need to do anything else. So that is our truss. Just because I'm not working on it now because I pulled myself off. Because we're working on Horizon, can I ask you all to please save in a moment? Because this is going to get weird. Right, I've done this and I'm just going to click close. You go, has that not crashed? It's because this is the project workspace. Can I ask you to save your project workspace? What I'll do is I'll just make one on the, because I'm going to upload this model. I thought it might be quite useful for you guys to just have a bit of a gander, so I'll call this truss and click save. What the project workspace does is gathers all the engineering data, gathers the geometry, and stores it all in a nice little package for us to be able to move around. If you bring in your own geometry across it, what it actually does is it will mess with other things. So it will actually make things even bigger, make storage space even bigger. But you do need to build a work folder for these types of things. But it's all stored from the engineering workspace. All extra files within it. If you're going to pass this between people, you must zip everything together because it is very file dependent. Right, so set up for the next step. I've got model. Right click on that model and I'm going to go to edit. Now this is going to step into the workspace, the actual simulation space. Because at the moment all we've done is just use the CAD, well I don't like calling it a CAD system because it's not really a good one, but I suppose it is a CAD system. You can use it for a CAD type method. Give it a minute, goes through the overall process, snap, there's the actual drawing. Brings in the geometry, brings in the cross section. So before we start setting this up, just want to introduce you all to how this thing's laid out. To navigate around it, middle mouse button to spin it round, to move in and out, obviously your normal mouse button, to bring it all back into view, right click and go to zoom to fit. Or you can do your typical view cursors, so you can go views, and I can go, oh, whatever really, whatever. So I'll just go zoom to fit again, and that is my geometry. Sadly though, I can't find a way of being able to highlight this so you can see this clearly. So from the project area, let's take a look at the geometry. Geometry is brought in. When it's brought in, it brings you a lot of details that come in with it. Units that it was brought in at, as you can imagine. Boundary box sizing, so how big is the actual component overall for its cross-sectional space. Properties of what's been brought in. Now this, you notice how it's got a mass attached. You kind of look and go, well, there's no geometry there, but there is. We'll get further down it. I can show you where that's coming from. So, starts with this. Body types that are in, basic geometries that are in, and overall how this thing has been represented. Now, if I go down next to the cross section, all it refers to is the cut type, the tube type, what it's actually been applied to, and that is it. Is there anything else that I missed on here? I just want to double check that I've not missed anything. I did miss one thing. So under line body with the geometry. The all important thing is, how is this behavior going to be simulated? I want it to be flexible, because when I apply it to it, I want it to deform around it. The reason that you've got flexible and rigid is because if you're looking at a particular body and you want to look at it in its worst case scenario, you can set all the components around them to be rigid. So when this thing hits, it hits an almost immovable object, and you can look at maximum damage that's occurring from it. But with this, I'm looking at flexible, so I'm not changing anything. All important here, material. Material comes in as default at structural steel. We are going to elaborate to this further, I think next week, just because I wanted to just get a good feel for the environment that I'm going to work in. I'm going to minimize that and minimize that. Then, coordinates-based measurement. The coordinates allows us to just give it a point of origin for beginning. But we can move this coordinate, we can make this coordinate move in particular ways. We can simulate a linear actuation motion. So if we know the displacement of that linear actuator, depending on the component, we can tell it which way it will move to look at the force as a resultant. But with this, because it's fixed to the wall and because it's a result of us applying 10 kilonewtons to it, it allows us to really look at the overall picture. So the mesh, the all-important mesh. I've elaborated to this further and further, but what I wanted to do is to just build in a little bit more. So I'm going to first right-click and I'm going to go to geometry, right-click, and I'm going to go to generate mesh. What you should see is something like that. This generate mesh, what it will do is it will give us some type of result. Now, the one thing that's different here, you notice how it's not triangulated. You notice how it doesn't look in particular ways. Now, how is it being seen is the all-important question. If I come back and go to my original crappy drawing and then just come back to here and then pull this out, I just want to just give you an idea of how this is actually working. So we know about this mesh, we know about how it's going to representatively move in space. But if I then bring this back across, snap it into here and get rid of this, and then copy, paste. So bring this into here, and then bring this into here like this. This is how the mesh is working. This has been notoriously named the linker mesh. So what it does is we provide the cross section. We give it an overall size, and then what the system will do is it will connect links across. So it will actually give a node, then an element, and apply that cross section and simply subtract between the two, and it will do the same again and again and again. So it doesn't need to apply the triangulation or hexagonal, anything like this. It doesn't need to apply that. It uses this straightforward. Now the issue is if this was to bend, if this was a bar, for example, and we were to bend it at a particular point, apologies, it's not the best drawing, I appreciate that, but if we were to bend this at a particular point, if you bend a bar, you know that you're going to get some radial type of resultant from actually bending it. It will bend in arcs, I should say. If we bend a bar in this case, what it actually bends with is straight lines, straight angles with it. However, if we're solving something like a truss, where we've only got nodal behaviors at these points, this type of system can do it incredibly well. So what it actually does is it doesn't use that triangulation, it uses what they call linkers, or at least what's nicknamed as a linking methodology, and it links the nodes together based on our cross-sectional value here. Now if I come on to my sizing, we're not building any specific meshes this week, but we will be building meshes to elaborate on things further, because this is just a basic geometry interface. But you'll notice here that I'm set to coarse. I can make this a medium result. So let me just generate that. Probably won't do much, no. And this is just because it's such a basic type of approach towards it. It doesn't need to be extremely sophisticated, because this is what this stuff was really designed around. So I'll switch that back, put it to there. So that is our mesh. We know that the linker will be alright for what we're trying to solve with. When we move further down, I am going to be introducing more and more frustrating geometries. We are going to be looking at the ASTM D38 standard. We're going to try and build a dog bone verification tool that we could easily apply to a machine and be able to validate that straight out. The frustrating thing is I now have this machine, but I don't have access to it, obviously, because of this position that we're in. Right, so come back. I'm going to bring that round like that, and we're now onto Zoom to Fit. Let's now set it up. I've rabbited on enough. Let's set it up. Static structural. Under my static structural, I can use my environment tools here if I want, but what I'm going to do is right click, I'm going to go insert, and with this I'm going to go fixed. Now under my fixed support, what it says is just click on something, tell us what's fixed. And let's just refer back to the drawing. I'm going to fix it at both points. Really, it's a roller, so I do really need to apply that, but for this, I know the type of result we're going to get. The thing is, at the moment, if you try to move across, you kind of look and go, it's not doing anything. It's just not working. Look over here. We've got tools we can use to click onto, ways of attaching to. We've got edges, so we could, if I click on edges for example, I could choose the entire edge to fix it. It's not that. I'm going to click on vertex, press Control, click the point to the top left, click the point to the bottom left, to the bottom of my vertical support. You must keep your finger on Control, or else what will happen is if I click on there, and then click on there, and then click on there, and then click on there, press Control, keep your finger on Control, and select that. So you've now got two selected. If you've done it right, this question mark, when I hit apply, should turn into a green tick. So click apply, turns into a green tick. If it's applied correctly, you'll get this blue point on top and bottom to tell you that there is a fixed point sitting there. Then finally, what we want to do is right click, go insert, come down to, where are we? Force. God, I went blind then. Force. I'm going to come all the way across. It is now just one point. It's our end point here. Click apply. And now we have this to deal with. Now, what we've got so far is we've got our fixed points here and here, and we just need to apply a 10 kilonewton load to the end of the truss to tell us if it's working like we think it will. You can use a few things. You've got vectors, which is a vector based on the geometry that it's coming from. It'll normally give you a normal to view, so it'll attempt to be perpendicular to the vector that you're applying. That's why at this point there you'll see that it just gives you a red spot, because it's a bit confused which way it's going. It owns the crap out of me as vectors, because you kind of look and go, am I going this way? So what I like to do is, if you see here you've got define by, I like to just use components. With components I can say a certain degree in all different elements. We're going to look at our datum here, our triad. A triad lets us know that we're going to be in the Y component. And For those of you who use SolidWorks, you've been spoiled with a lot of things. What I mean by that, SolidWorks, you click a direction, which way is that force going? With this, it is true to the actual datum. So, obviously, if I was 10,000 here, it will be going upwards. If I go minus 10,000, 10 kilonewtons on the end, it gives me an arrow. If you've applied it correctly, you should get a green tick on the design tree. You should get an arrow pointing downwards. And again, to change by define by, all you simply do is drop the arrow here to vector or components. I've done it by components. If you are prone to wanting to use vectors, please do use vectors, but I always use components because I just like to know it's moving in the right direction. What I'll do is quickly hit save. And now I'm in a great position. Everything's in there. What I'll do is I'm just going to solve it. So if I hit solve, it will show me if it's worked. I've got green tick on my solution. I've got a green tick on my solution information, so it tells me that there was no problem in what I did. And now I can look at any types of results I want to. The most important one for me is the stress. I'm going to use a tool on here called the beam tool. It'll allow me to just elaborate about what's happening to these beams. So zoom that to fit. That's where we're sitting. And all I'm going to do is right click on solution, go to insert, and we've got beam results. But what I'm interested in is just looking at the beam in itself. So I'm going to go on beam, and you'll notice here that they've got yellow lightning bolts. The only reason I've done it this way, because for some of you will know you could apply it before, but I've done it this way because some of you might not know that you can reevaluate from the present solution that you did. So on here, if I right click, go to evaluate all results, let's have a look. Direct stress. So it's giving my deflection. If I click on animation, it just shows me how it moves. You can see the concentrations to the top. Obviously in red, it is maximum force in tension. Obviously in blue, it's maximum force in compression. So it's given us an awful lot, massive amounts. Now what's important with this, and where people fall on their faces a lot with this, is here. Unless I offer something to you to show that it's doing the job right, you don't know for sure that them values are even remotely correct. You don't know what you're looking at. You don't know that I know what I've been doing. So if we look, now ANSYS, this is one of the things I've always liked about ANSYS, really liked about ANSYS. If you look here, we've got these bands, and you'll notice where it's red, it's 1.2 to 1.5. First things first, let's take a look at our initial result calculation, what we'd suggested. So if I come back and based on the calculation, oh, not that one, this one, and we bring it back across, we know that we were talking, which was DE, maximum compression should be 18 kilonewtons, and we know that that's a typo there. I just noticed that. We know that CD. Oh no, it's not. We know that CD is 15 kilonewtons in tension. So we come back across. We look here. We've got 1.5. But if I knock that point to 15 to the power of 6, we have 15.9 kilonewtons of force in tension. If you look beneath, now this is what's interesting. You look there, again, let's just operate to move in that decimal place. So I go 18 to the power of 6. So 19 to the power of 6, 19.1 kilonewtons of force in compression. Now, you come back and you kind of go, yeah, well, that's actually out. Now, this is where ANSYS really shines, and I do quite like this. Remember, right at the start of all this, start to discuss with you about the idea of error. This is simply the error of the relationship of these nodes, how they're talking to each other. Simply that, all the way through. ANSYS literally say, if you have a calculated value between 1.2 and 1.59, you're on the right ballpark. Because their error is recorded between 1.2 to 1.5. So in other words, we are in that range. So it means that ANSYS' result is giving us something that is usable. But they're actually acknowledging that there is error there. They're acknowledging that it could be refined further. It could be refined further. So if you look here, now arguably there could be a mesh maybe too high. The subdivisions of linkers may be too high. We may need to bring this down slightly because we may be getting over a behavior of what we should be genuinely getting. This is where it becomes very hit and miss with it, and you do modify that mesh a little bit further. But you look beneath, we've got that minus 1.5 and 1.9. Again, we're inside of that all-important value that we'd calculated, being 15 kilonewtons. So again, our lower value here to our upper value here is where we'd operated to. Now, if we want to look at refining this further, now I'm aware of that we're getting to 20 to 12, so I'm not going to go into too much of this, but if we want to refine this further, what I could start to do now is look at my relevance. I'm not going to even refine this mesh. I'm not going to play around with this mesh too much. I'm going to just bring in a little bit more of accuracy. So the relevant solving center, I'm going to go medium, and the span angles we are going to refine. We are going to cover these a bit more in depth, just because I know I've not covered that as of yet. Now let's update that mesh. You see now it's even more subdivided, but if I run this, this may return even more inaccuracies within it. When I said before, people spend months and months looking at the most accurate way of giving them a good representation of what's going on. It kind of, I mean, look at that. Not much change at all in each types of meshing procedures. But we're still within that ballpark figure. We're still at that right point. There is error still there, but there is a lot of things that we could discuss further. Another option may be to bring that mesh down a little bit, just to look at the solution that we're getting. I mean, I'm happy that the result sits there, because it does show that ANSYS has given us something useful, but it would be nice to tidy that up even more. Right. If you've not done already, can I please ask you to save that? I'm going to save this myself. I am going to upload this to Teams and just call this Truss. The equivalent example, what I did in Console yesterday, I've also uploaded, called that Truss as well. All the videos are on Team. I mean, on stream. So you are welcome to take a look at both, just to have a bit of a feel around with both. For anybody who's interested in the use of Console, Console is available on Citrix. So the UCLAN remote access Console is available at that point. It's actually not on Horizon. So ANSYS is for Horizon and Citrix is for Console. There's no reason for that. Nathalie, who runs the license, she just prefers Citrix as opposed to Horizon. So that's all that is. Is there any burning questions about what we've done? Oh, shoot. I've just seen that out completely. Okay, then that's great. So I'm going to close that. I'm just going to stop on my recording because that is all I really wanted to do today. What we are going to do moving into next week is we're going to look a little bit further at this. This is our engineering data, but this is the project data. We're going to dive a little bit deeper and go to engineering data sources, where we can look at our libraries for different types of materials and what we can use with that. We're going to stay with this verification a bit more. I'm going to give you a classic example which came out of Marin mountain bikes, where they were interested in verifying a particular material that they wanted to use for their cross members of their bikes. Got a great example with that. And depending on the speed that we move at next week, because I don't want to rush through this, but depending on the speed that we move at next week, I'd like to move on to the dog bone example. So the dog bone pull example, looking at material verification. Again, we will be calculating that a little bit more in depth. So the verification next week will be calculating the surface stresses around the pipe. And with the dog bone, we'll be looking at a stress, we'll be looking at strain, we'll be looking at key points for failures, and we'll try and calculate them out, and then we're going to use ANSYS to try and tell us if ANSYS can do what we want it to. I will just stop recording.